Okay, it's changing here, but it's not changing there.
Is it on the wrong screen?
Let me see if I can.
Everybody on Zoom can see what it's doing.
Is it on the right screen?
Oh, the other one's gone.
Yeah.
Are you still able to see the screen, people online?
Negative. We've just lost the screen, but we can hear your voice.
Okay.
And we can see you.
I'm just going to scan the entire screen. So it's okay. Let's see. Oh,
Yep, we can see your screen again. Thank you.
Yeah, I think the problem is I lose control of the slides once it goes there, which is what I just did.
Oh, yeah.
We're on to the second slide now. Yep.
Okay, good. Yeah, I think we're good to go now, I think, looks like. Yeah. Okay, so the road plan is to talk a little bit about why do we need lithium, and then talk about where do we find them. So talking more about the resources that we currently get lithium from. And then finally, this is probably where my expertise come in. Why do we find the lithium where we find them? Because my expertise is basically looking at how elements kind of move through rocks and basically the earth. And so hopefully we will get some idea there. So in terms of lithium usage, this is a slide kind of showing the usage as of 2022 in terms of percentage of lithium that's used. As you can see now, 80% of the usage is for batteries, including the batteries that we use in consumer electronics, as well as for electric vehicles and also for storage. But lithium is a pretty versatile element that's used for many other purposes. It's used for coating ceramics, which make them heat resistant. Also for making all types of glasses, where it's kind of used as a flux. It's used in lubricating greases because it's used as a thickener. And then also something that most of you are probably familiar with is it's used in continuous casting process fluxes for steel making and a whole bunch of other uses as well. Now, if you look back to the usage in 2000, you can see the transition that has taken place. At that time, we were only using lithium in non-rechargeable consumer batteries. And so you can see that big change is kind of driven by the usage of batteries in electric cars and energy storage systems. And the reason for that is pretty simple. Lithium is the third lightest element in the periodic table, right? So batteries made with lithium are quite a bit lighter. So that is an advantage feature. So if you were to compare internal combustion engine cars with electric cars, most electric batteries use about anywhere from 8 to 10 kilograms of lithium, right? And so that's where the usage is going to be happening in the future. Just to get an idea of how much lithium is used currently, so it's about 140,000 tons of lithium used in all the uses that we just talked about. Now, in terms of projection, so the projected use of lithium is going to be much, much higher than that. So this is the projected estimate for lithium usage, more than 5 times from 2023 levels by 2030, and probably about 15 times compared to 2023 levels by 2040. And so that is a huge increase in demand that's projected. Maybe I should kind of get rid of this. Yeah.
Why was manganese so high?
Manganese is also part of the lithium batteries. Some of the batteries uses manganese as well. Yeah. So lithium, for all the different uses that we talked about, is used in different ways. So we need to extract lithium, and some of the lithium that comes from rocks in the form of mineral concentrates can only be used for certain purposes, but for other purposes, they need to be refined into these different products. Most commonly, lithium carbonate, right, which is used in some batteries, and obviously lithium is also used in pharmaceutical application because it is a mood stabilizer, which has been used to treat bipolar disease since the 1950s. But modern, the most recent batteries need lithium in the form of lithium hydroxide, right? Because there's a lot more impurities in lithium carbonate. So to make the batteries more efficient, you need lithium hydroxide. And for other purposes, we use different forms of lithium as well, sometimes lithium chloride and metallic lithium. So if you look at the present extraction of lithium in terms of where they come from, 3 countries dominate the mining of lithium, if you will. And up until recently, Australia used to be more than 50%, but it's currently just below 50%. But if you look at those 3 countries, Australia, Chile, and China, they make up more than 75% of the lithium that's used currently. Okay, so there's a monopoly there. And the picture changes completely when you switch to refining lithium into those different products, which is used in the for the various applications. Then China becomes really dominant. And you can see that Australia kind of disappears from the picture just because they mine the lithium and send those mineral concentrates to China for refining, right? And so Chile still refines some, and Argentina comes into play a little bit. So in future, it looks like most of the lithium might come from what people call like the lithium triangle, which includes Chile, Bolivia, and Argentina. The production from Bolivia and Argentina is currently pretty low, but that is likely to pick up. But as you can see, there is a monopoly both in the mining of the resources as well as in refining. And that has sent some supply chain concerns for people around the world, right, who are depending on lithium. So the supply risk for lithium is considered to be pretty high, as well as there is a geopolitical risk. If countries stop sharing the lithium, then you can't have those industries that need lithium usage, right? And so which is the reason why if you look at the critical mineral list of most countries, lithium will feature in that list, including this fancy list of Canada, which includes 32 minerals, and lithium is one of the most prominent minerals in there. So where do we find lithium? Well, they come from 2 main sources today. Some comes from rocks, so basically minerals within the rocks. And the other main source is brines, so basically highly saline fluids, right? So think of much, much more saline than seawater, right? So let's look at some details of these. So I'm a rock expert, so this is where I'm more comfortable talking about. So the lithium from rocks comes from this rock type called pegmatite. Okay, so pegmatite is a rock term that we geologists use for really coarse-grained rocks. So they have like really big crystals. Okay, so the technical definition is that most of these crystals in pegmatites are typically larger than 5 centimeters in length. Okay. If you compare that with most common rocks, they are much, much finer grained. So they're usually roughly around, let's say, a centimeter or so maximum size of the crystals. So they're unusually large crystals. The other thing about these lithium-rich pegmatites is that they come from a specific type of pegmatite with granitic compositions. So I think people are familiar likely with the rock granite, right, which is used as a countertop, right? But geologically speaking, we think of granite in terms of the minerals it contains, but you can also think in terms of its chemical composition, which is what I tried to show here. Most magmas are composed of dominantly of silica. If you look at rocks like basalts, which is formed from the lavas that erupt in places like Hawaii, they have nearly about 50% silica. Okay, and that's the amount of silica that you find in them. But granite, on the other hand, contains nearly, let's say, more than 60 to 70% silica, or sometimes even 75% silica. So that's what I mean by granitic composition. So most of these pegmatites, those coarse rocks in which we mine lithium from, comes from these pegmatites of granitic composition, so silica-rich rocks. But the trick is that not every pegmatite contains lithium. So the pegmatites can be grouped into two broad families. One is called the lithium, cesium, tantalum family pegmatites, which are the ones that contain obviously lots of lithium. But there is also this other group called niobium, yttrium, fluorine family pegmatites, and they don't contain appreciable quantities of lithium. So that's an interesting question as to why do these different pegmatites have different concentrations of lithium. The other importance of pegmatite is you might have seen those gorgeous mineral specimens in stores, and most of those comes from pegmatites, right? Because they form these really large crystals. So here, for example, on the right-hand side, so this is a tourmaline, and that is a mineral called spodumene, which is actually the most sought after mineral for lithium extraction. But this one is obviously a gem quality spodumene, right? Pretty nice and crystalline. Okay, and that's not what typically we mine. Typically, the spodumene that we mine looks like this. Okay, but it contains a lot of lithium, as we will see shortly. And so the size of these can vary quite a bit. Unfortunately, there is no scale here. These are all individual crystals of spodumene. Here is one from a mine in South Dakota. So again, these are single crystals of spodumene. Here's a tree for scale. So these are meters long, right? And why is spodumene really important? If you look at its chemical composition, so lithium is one of the main elements in them, and it contains about 6 to 9% lithium, and that's a lot of lithium. What's listed here is some of the other lithium-bearing minerals that could also be used to extract lithium. But as I mentioned, spodumene is the most sought-after mineral, along with this second mineral listed here called petalite for lithium extraction from the rocks. The other source of lithium, as I mentioned, comes from these fluids, highly saline fluids, which we call brines. And so in South America, these brines are extracted and flooded onto these ponds, where they are evaporated over a period of somewhere from a year to sometimes almost 2 years to concentrate the lithium and extract from it. So that's a process in which lithium is currently extracted from these big salt lakes. If you look at the present day global distribution between these two different sources, so in this map, shown on red are the pegmatite lithium, so basically coming from those hard rocks, right, from those rocks that were produced from magma. and the ones in blue are the ones that comes from the brine. So in South America, lithium is primarily extracted from those lithium brines, whereas the most common source is actually those hard rock pegmatites. Okay. In terms of the current production, pegmatites are probably slightly more, probably about a bit more than 50% of all the lithium comes from those rocks. But the brines, as we will see, are kind of picking up in terms of their production. So if you are an economic geologist, when you think about a mineral deposits, there are two things that you look for: the grade of the deposit, which is a measure of how much lithium is in the rocks that you process. That's kind of shown here on the vertical axis. And on the horizontal axis is basically the resource or reserve, which is the total amount of lithium that you can get from a deposit, right? From that particular area. So again, if you look at the two types of deposits, what's shown in the blues are those rock deposits.
Excuse me, can I just ask you to try and speak a bit more into the microphone? We seem to have lost the sound, or at least it's much weaker now. So that's a request to the speaker. Thank you.
Thank you. I think the mic fell down, which is why putting it back on.
Okay, thank you.
Okay, so we have on blue the pegmatite deposits, right? So as you can see, they are high-grade deposits. So Tanko is a pegmatite in Manitoba, which has been mined for lithium as well as cesium and tantalum. So as you can see, they contain about 1.2 weight% lithium, right? And as you can see, most of these pegmatites have high grade, so they're actually really good to work with, right? Because you can extract quite a bit of lithium from them. The ones on these black crosses are the brine lithium, including the most famous one from Chile is the Atacama Salar deposit. So they contain much lower grades, right? So on average, they contain about 0.28% or about 2,000 ppm, right? Whereas here we're looking at nearly 12,000 ppm in the pegmatites. But the solar deposits, the brine deposits, they are really large, right? So they constitute a big resource. And that's why I think that the brine lithium is going to be overtaking probably the pegmatites as a source in the long term. But it's good to kind of remember these numbers, right? So we have 2,000 ppm lithium in these brines and 12,000 ppm in these pegmatites. So now we'll go into the last part of the talk where we're going to talk about why do we find the lithium where we find it, right? So we'll first talk about the abundance of lithium in the solar system, which is kind of set by basically how much lithium is produced within the stars, right? And so we can kind of gauge this by looking at the composition of the sun, right? And by measuring the composition of the sun, we get an estimate of how much lithium is in the solar system, because in the formation of our solar system, nearly 98% of that mass of the solar system became the sun. So cosmochemists usually use elemental abundances, report elemental abundances relative to about 1 million atoms of silicon. So that's basically, so this is a kind of logarithmic scale. So basically that's 1 million atoms of silicon, right? So if you compare to that, lithium is not that abundant. Okay, so if you have 1 million atoms of silicon, you're looking at about 100 atoms of lithium. So it's not a very rich element in the solar system. And that's just simply because that's actually kind of unusual, because as you can see with this pattern, so this is elements arranged in their, according to their atomic number. Usually the heavier elements are less abundant than the lighter elements. Lithium, even though it's a lighter element, it's actually much lower in abundance. And that's just simply because lithium is usually destroyed within stars like our sun. Right? So any lithium that's there, it's actually destroyed. So that is a problem. So our best model for the formation of the Earth is that Earth formed from materials that are very similar in composition to the sun, and that is similar to the composition of some of the meteorites that comes from the space, which we can measure, right? So as you know, the Earth is composed of different layers, right? And we have a core, a mantle, and the crust upon which we live. So this is kind of like a cross section, just kind of showing mantle, which is probably the biggest voluminous reservoir on Earth. And then the upper crust kind of shown in this really tan color. So if you take the composition or the abundance of lithium that's present in the chondritic meteorites and also that of the sun, the mantle contains about 1.7 to 1.9 parts per million lithium. Okay, but when you come to the crust, the abundance increases a little bit to about 17 parts per million. So that's an interesting transition that occurs, which hopefully we can make sense of. By the way, the amount of lithium that's in the oceans is about 0.2 ppm. Okay, so if you compare this with the amount of lithium that's in the deposits, right? It's 2,000 ppm in the brine and 12,000 ppm in the brine, in the pegmatite rock deposits. You need to basically enrich the lithium by some mechanism to make it that rich. So if you look at the LCT family pegmatite, which contains a lot more other useful metals in addition to lithium. But as I mentioned, the key minerals are spodumene and petalite, right? And they contain, anywhere from 6 to 4% lithium, which is super rich. So from the Earth's crust, which has 17 ppm, we're actually somehow enriched it to that levels of ppm. So remember, in the pegmatites, we need to produce these minerals, spodumene and petalite. So this is a phase diagram, right? Showing the stability of these minerals as a function of pressure and temperature. We can sort of ignore the pressure here, but importantly, most of these pegmatites, because they're formed from those granitic magmas, right? So their formation temperatures are estimated to be around, let's say, 500 degrees Celsius or so. Okay, so under those conditions, if you want to form petalite and spodumene, what you need to do then is you need to enrich the lithium in the magma to the point where it can form these minerals with lithium as a main component in them, right? Otherwise, what's going to happen is if you don't enrich it, lithium is going to be dispersed in all the other different minerals, and you don't have high concentrations of them in any mineral. Okay, so the diagram on the right-hand side kind of shows how much lithium is required to reach those saturations to crystallize these minerals, okay, as a function of temperature. So you can read the temperatures at the top here. So as you can see, the lithium solubility in the magmas increases as a function of temperature. But let's say at around 500 degrees, we need to enrich the lithium to maybe about 7,000 or more ppm for it to form petalites and spodumenes. Okay, so remember our crust mantle has 1.7 ppm, the crust has 17 ppm, and from there we need to get to about, let's say, 7,500 ppm before we can actually crystallize these minerals. So how do we do that? Well, you start off with a lithium-bearing magma, right? So imagine you have a lithium-bearing magma in which the red is lithium, and you have other elements in yellow. Okay. So you bring that magma up and you cool it, and once you cool the magma, it starts crystallizing. So lithium is one element that really doesn't like to go into many minerals. We call them incompatible elements. They don't really quite fit into the mineral structures that well. Okay. So imagine crystals forming from the magma, so which I kind of try to show schematically here as these rectangles. And so they are taking in those yellow elements, which is anything other than lithium. So they are preferentially taking in those elements into the structure and only taking in a little bit of lithium. So in the process, what happens is that the rest of the magma becomes more lithium rich. Right? So the more the crystallization occurs, then what we call the residual magma becomes more and more lithium rich. So this is kind of shown schematically again here. So if you start off with a magma, right? So 0 here means it hasn't crystallized at all. 100% means it's 100% crystallized into different minerals. And this is kind of showing how lithium will evolve. And that dashed line is basically the concentration of lithium you need to reach before you can form spodumene and petalite. Yeah. So you start off with, let's say, 17 ppm in a granitic type of magma. But as you crystallize it, because all the other minerals are pulling out other elements, the lithium concentration goes up. And during the last stages of the crystallization of the magma is when lithium gets to those high amounts where you can actually find those minerals. So that's a problem, right? Because we only get to high levels of lithium during the last stages of crystallization of a magma. So we're talking about more than 90% crystallization of a magma, right? So if you then start with a granitic magma, only the last 10% of it actually contains enough lithium to form a mineral deposit. Okay. Interestingly, along with lithium, another element or elemental combination that increases in magma during crystallization is water. Right? Water is also something that minerals don't really like to take into its structure. So as the magma crystallizes, the water composition also goes up. So the last liquid that's remaining in a granite is rich in lithium, along with other elements like lithium, which doesn't like to go into the minerals, and also water. Okay? And these magmas and these last little liquids, because it contains a lot of water, it can actually intrude into the surrounding rocks. And that's where you form the pegmatites. And the reason why you form those large crystals is because formation of crystals involves movement of elements, ions, to a site where the crystals can grow, right? And the elements simply move much, much better if there is lots of water in that liquid. So in those water-rich liquid, you form these really, really big crystals. And that's why we sometimes get those really nice looking crystals as well in the pegmatites. So if you were to look at this in a field setting schematically, you start with a parental granite, right? Which you crystallize, you end up with a residual liquid, not large volume, but that liquid, because it's water rich, is going to now go into the surrounding rocks, and it usually preferentially uses some of the fractures and stuff that you have in the rock. But as I mentioned, the lithium concentration only becomes so high in those last stages of crystallization. And so there is a zonation in the distribution of these pegmatites. So all these blue things are different pegmatites, but only the pegmatites that are actually much further from the parental granite contains enough lithium. So those other pegmatites, they don't have high concentrations of lithium. They might contain other elements or minerals that are quite valuable, but they don't have enough lithium. And so that's basically the challenge in mineral exploration involving pegmatites, right? Because initially you need a granitic magma, And turns out that not every granite has that high lithium to start with. And then you also need to map out the different zonations where these pegmatites form, and you have to find those pegmatites in the farther reaches of that emplacement scenario to find the lithium. So how do we go from 1.7 ppm lithium to 17 ppm lithium in the crust, and also to more than 10,000 ppm in these deposits? Well, the process that I described, right, which is kind of similar to zone refining, which some of you might be used in metallurgy. The same process also occurs during melting of rocks. So we melt mantle to produce magmas, and which is essentially what becomes the crust of the earth. And it's a process that's still continuing, right? So when those magmas are erupting in Hawaii, those magmas are coming from the Earth's mantle. So as we said, when you melt the mantle, you don't melt the mantle completely. You're only melting it partially, which means you're possibly melting perhaps 10 to 20% of the mantle of that region. So as I mentioned, lithium really doesn't like to be inside the minerals, right? Because minerals can't really hold on to them that well, right? It doesn't fit. So when the mantle melts and it forms a magma, lithium is going to jump into the magma and take a ride to the crust, right? And then if you remelt that crust again, now the next magma that you generate from that is going to contain more lithium. And if you remelt that again, then you have more lithium. And then once you have those lithium-rich magmas, then come to shallower crust and undergo what we discussed in terms of crystallization, and you can get to those high levels of lithium. So it's kind of like a natural refining process that the earth does for us, right? And in fact, the earth does this for many metals that we use in nature, right? Which originally don't have high concentrations in the crust. And this is how we kind of enrich them. Now, when you go to the brines, once we understand this process of enrichment that occurs in the crust and in magmas, it becomes easier because the Chilean brines basically form in these closed basins. So basically these are lakes, right, which do not have outlets. So, but the source of water in these lakes is precipitation falling on volcanic rocks in Chile. So those rocks contain some lithium. So the water leaches lithium. Lithium is pretty soluble. And so it kind of deposits that lithium in the lake. And because the lake doesn't have any water and this is a pretty arid climate, it basically sits there and evaporates, and the concentration of the lithium get to as high as 1400 milligram per liter just from that evaporation process through time. Okay, but even that is not sufficient for us to extract lithium directly. We still need to concentrate it further to get to those levels, like let's say 10,000 or so, right? And that's why they pump this lake into ponds and let it evaporate for a year to concentrate lithium and produce lithium carbonate from them. There are a couple of other unusual deposits now that are being discovered. These are lithium-bearing clay minerals. And these are quite different. Clays have a very layered structure, so they kind of have sheet-like structure, just like, you know, pages in a book. And clays have really unsaturated, let's say, bonds, and so they have the ability to exchange ions with water, right? And so some of these clay minerals, like diaterite and hectorite, they do preferentially take lithium from the solutions they are in contact with. And so they get enriched with lithium quite a bit. So this diaterite is only found in one location Jadar Basin in Serbia, but it contains about 7% lithium oxide. So that's pretty high, even higher than the spodumene, right? But the hectorite clay is what they mine in Nevada, right? But there, the clays were formed through, again, alteration of volcanic rocks. And basically, when alteration occurs, you form these clay minerals. And from those waters that contains the lithium, the clays basically suck in the lithium, and that's how they get enriched. Okay, I think for the last couple of slides,
Quick question.
yeah.
A couple of years ago, there was a project run extracted lithium.
Yeah, so the question was about extracting lithium from oil sands. Just from the brines, I think. Yeah, and I think in the next slide, I'll talk about it. Okay, yeah. So yeah, we should talk a little bit about Canadian lithium projects. So there are a few, as you can see here. The ones in green, or actually they're all in green now, except for these two in Alberta, which is our brine projects, right, from formation brines. All the others are actually rock projects. So basically looking for those spodumene. And the only, well, there is a couple of producing mines, the Tanko mine in Manitoba and the North American lithium mine in Quebec. Other than that, the other projects are in various stages of development. Canada obviously is not a big player in lithium, right? We only produce about 0.4% of the lithium that's produced today, but we have 3.6% of world reserves. I would say that's an underestimate of what we have because we haven't specifically done enough exploration for lithium yet, right? Because what we have here, where all these rock projects are, that's the Canadian Shield, right? And one of the main rock types in the Canadian Shield is granites. And once you have those large granites, they are likely to contain pegmatites around them, right? So we just simply haven't explored for them yet. Now, a word on the lithium brines in Alberta, just to compare the amount of lithium they contain, they have very low lithium, okay? So they have, that's about 20 ppm, right? It can range up to 140 ppm in some stratigraphic levels, some rock layers, but when you compare that to the mines in the brines in Chile, they're much, much lower in lithium abundance, right? And just for, again, comparison, the average seawater is 0.2 milligrams or 2.2 ppm. So how did these brines form? There are various ideas, but we think that mostly those resulted from evaporative concentration of seawater, right? So you're basically evaporating that seawater basically to generate that much lithium, right? But it's also possible that they could have formed some, there is some sources from leaching the rocks, yeah? But the abundance of those, the lithium in those brines are very, very low. So we cannot really use the technique they use in South America where you pump them out into big ponds. A, because it's very environmentally unfriendly, right? Huge problems with that. But also, we're going to have to basically evaporate huge oceans or lakes of water to get a little bit of lithium. And that's why people now are talking about electrochemical processes where we are directly extracting lithium from the brine, right? And some of those techniques are now becoming viable where you can use production wells, right? Either that's used for geothermal purposes or for oil and gas production, use those brines, extract lithium directly from them and pump them back down. But the problem is that if I find is once that technology is established, they're going to go and take it to the Atacama brines, right? Why would they want to do that in the Alberta brines where there's only 20 milligrams per liter lithium, right? So my final thoughts is that despite the wide distribution of lithium in rocks, high concentrations of lithium are limited. And in the long term, we're going to likely have shortage of lithium. Yeah. In the long term, that may render some low-grade deposits like the oil field brines economically viable, right? But in the short term, I think the hard rock lithium sources will likely be needed to meet the demand in the next couple of decades. And that means we need better exploration models for looking at rock-based lithium. And that's my pitch to put more investment in geology. Okay, I'll stop there. Thanks for listening.
Thank you very much. It was a great presentation. Questions? Don't know how we're going to manage the online
Questions on the chat, weren't there? So
let's start with the
start in house. Just a comment, we had a talk this week internally in our company about lithium extraction and then pushing the brine-based systems. But you just blown that out of the water. Thank you very much.
It is viable, right? But once that technology is available, then the question is, why would you want to do it on a brine with such low concentrations than high concentrations? Yeah.
I've got a question now. I heard that Africa also has lithium. I didn't see the list in your list you put up.
Yeah, so the question was, does Africa have lithium deposits? They should. So just like the Canadian Shield, Africa also has shield rocks. South Africa, they have something called Capwall Craton. In Zimbabwe, they have Zimbabwe Craton. And likewise, there are these cratonic nuclei. And they do have lots of granites there, right? And then granites would then also contain pegmatites associated with it. It's just that people haven't yet started looking actively for lithium, right? People were looking for other metals up until now, but those exploration projects are likely going to take off, and we are likely to see more rock-based lithium projects. On that vein, you probably know that the lithium prices kind of crashed, right? A couple of years ago. And that is because a lot of these rock-based lithium was becoming available.
Do you have a question?
Yeah, become very popular these days to talk about rare earth minerals. One of them, but the refining, I don't know how much time or chance you have to look at that, Rajeev, but clear China has a very strong market share. Is it just dirtiness? Is there high tech? I mean, copper used to be classically done and zinc here, just very much processed. What happened?
Yeah, so I think, so the question was basically, is the refining of lithium a dirty process, or is it, or why is China monopolizing that field? It does involve acid leaching, right? So basically for the rock-based refining, so you have to roast those ores with sulfuric acid, and then you precipitate lithium carbonate from them. So that's basically the first step. That by itself doesn't seem, compared to rare earth elements, which seem to be a much more dirty process, the lithium extraction is not that much. So now I think US is kind of starting to build some processing plant. And so I would imagine other countries will as well. Yeah. but compared to like rare earth, it's a much dirty process, I think. Yeah.
How efficient is the recycling process?
Yeah, great question. So the question was, how efficient is recycling? So that is going to become an important source in future, but we just haven't built up enough, used lithium, let's say metal to do that. So currently the rate of lithium recycling is less than 1%. Okay, but the potential could be as high as 80% from these batteries, or even higher, right? So, but we need to create that scrap first.
There's a question online said, what about the stability? The lithium in my car battery is surrounded by iron.
But
Oh, can we get the chat?
I'm not a big battery person, so I hope I
Can
can
we go down?
make sense of it.
Can we go down, Gobin?
I think I was asking the question because lithium seems to be unstable in some ways, and fires around lithium batteries are a big concern, whether it's in cars or cell phones. So I just wondered whether in the mining process, whether that same hazard exists, mining or processing.
No, it doesn't, because lithium, the reason why if it's in the metallic form, right, and if it's exposed to oxygen, it'll react, because it's, if you remember your periodic table, it's on the first group, right? So those are very reactive metals. And so if they exist in the metallic form, they can react. But in these mines, they are mostly present as silicate minerals. So that's not an issue with mining.
Any other questions in the room?
A lot of the facts that you gave us down there were quite popular with growing the wine. Like Centenario and Cereal, Goto. Can lithium be used for winemaking?
So the question was, can lithium be used for winemaking? I'm not quite sure. But as I mentioned at the beginning, sort of lithium is used as a treatment, right, for bipolar disease. And what people have found in studies is that they looked at people who consumed water with lithium and without lithium, and the incidence of mental disease was actually kind of high where people did not have enough water, lithium in the water, right? I don't know if this is going to make your wine any sweeter, but I don't think there is any harm if you were to put some lithium in there, I would say, yeah.
Okay, so I'm going to close the meeting there. Rajeev, that was a great talk. Thank you very much. Very informative. And thank you for staying calm with all of the technical.
Oh, no worries. Yeah.
We'd like to present you with a certificate in this envelope. It's from operating eyesight, and the person with the certificate has gained eyesight because of your talk tonight.
Oh, thank you.
So thank you very much.
Online people can sign off.